So in part one of the video, we learned to identify basic redox reactions between metals and nonmetals. But once we kind of take the metals and the nonmetals out of the mix, it becomes a little bit more difficult for us to understand what's being oxidized and what's being reduced. So that's where this part of the video, part two, we're going to focus on how to assign oxidation numbers to help us a little bit more with keeping track of the electrons. So what is an oxidation number? An oxidation number is going to be a positive or negative number that we assign to an atom, and that's going to help us keep track of how electrons are moving in that redox reaction. So these oxidation numbers are going to help us figure out what's being oxidized and what's being reduced as the reaction is taking place. So our focus for this video is to learn the rules to assign them to an atom in a compound. We're not going to focus on how to use them at all. That's going to be what we'll talk about tomorrow. So our goal for just this portion of the video now is to understand the 6 rules that we use when assigning oxidation numbers. So, rule number 1, the oxidation number of a free element is 0. What do we mean by free element? A free element is going to be anything that stands by itself. So these are things that are not part of a compound. So these are things that are individual by themselves, not part of a compound. So examples would be all of your Hankel-Briffs. So anytime you see H2, O2, N2, Cl2, Br2, I2, F2 by itself, the oxidation number we would give is 0. All of your solid metals, like Na from our last example, or Ag, or Mg, or Al, any solid metal by itself is a free element. So anything that is not part of a compound by itself, we give an oxidation number of 0. Rule number 2. If I am a metal or nonmetal ion, so I'm something that's now part of a compound that is ionic. If I'm a metal or nonmetal ion, my oxidation number is going to be equal to my charge. And how I figure that out is by using my periodic table. So to figure out the oxidation number, I just have to look at the periodic table and figure out what its charge is. So our first example, NaCl. Na is in column 1. We know that makes it a +1 ion. So we would give Na an oxidation number of +1. Cl is in column 7. We know that makes a -1 ion. So we would give Cl an oxidation number of -1. If we look at the next example, Mg is in column 2. So that would make it a +2 ion. So its oxidation number would be +2. O is in column 6, which is -2 ions. So its oxidation number would be -2. Al is in column 3. So that would make it be a +3 ion and a +3 oxidation number. N is in column 5, which makes it a -3 ion and a -3 oxidation number. So if I'm a metal or nonmetal ion, my oxidation number is simply whatever my charge is as determined by your periodic table. Now oxygen's a little bit more tricky because he makes both ionic compounds and covalent compounds. So we do have some rules for oxygen. Anytime oxygen is in a compound, its oxidation number is going to be -2 unless it's a peroxide where it goes from a -2 to a -1. Now, if it's a peroxide, I would tell you. So I would not hide that from you. I would not be like, ha, guess if it's a peroxide or not. Nope, nope. I would tell you this guy is a peroxide. So you would know that oxygen is a -1 in that compound. Now, because oxygen has a couple of different oxidation numbers, it can be seen with different numbers in different situations. So we know O2, oxygen, in its free elemental form, from rule 1, would have an oxidation number of 0. H2O is a compound that is not a peroxide, so we would assign oxygen with an oxidation number of -2 in this compound. And H2O2 is a peroxide, so we would assign oxygen with a -1 oxidation number in this compound. So depending on how we find our oxygen, that's going to determine what type of oxidation number we give it. If it's a free element, it would get an oxidation number of 0. If it's in a regular old compound, it would get a -2. If it's in a peroxide, it would get a -1. So oxygen can have a couple of different oxidation numbers. Hydrogen, on the other hand, will always get an oxidation number of +1 in compounds. So anytime hydrogen is in a compound, we give it an oxidation number of +1. It does not matter who it's hooked up with. So in H2O, its oxidation number would be +1. In HI, its oxidation number would be +1. In NH3, its oxidation number would be +1. It does not matter what it's with. It will be +1 every single time, no matter what. So these first couple of rules are going to help us with the last two, which are the most important, because these deal with more complicated compounds. So to review, free elements get an oxidation number of 0. Metal and nonmetal ions get an oxidation number equal to their charge. Oxygen is going to be -2 in compounds unless it's a peroxide where it's -1. And hydrogen will always be +1 in a compound for its oxidation number. Number 5 talks about compounds, and this can be any compound. It can be an ionic compound, it can be a covalent compound, it does not matter. So for any neutral compound, meaning ionic or covalent, the sum of the oxidation numbers must equal 0. So what that means is when I add the oxidation numbers up, it must get me to a total of 0 for that compound. One very important thing is when you assign oxidation numbers, you assign it to the individual atom. So for example, if we look at CuCl2, we're going to give Cu an oxidation number and we're going to give Cl an oxidation number. But because there's 2 of them in that compound, that means we have to take into consideration how many Cl's we have total. But we're just going to assign the Cu and the Cl with their oxidation number. So when I have compounds, here's what I like to do. I like to write my oxidation numbers up top, and I like to keep track of the total oxidation number on the bottom. This is the guy that we care about, so he's the important one. We care about, this top oxidation number, because that's the one that we look at to help us figure out what's oxidized and what's reduced, and we'll talk about that more tomorrow. The total oxidation number just helps us get these guys up here, so it's kind of like determining ion charge a little bit. So if we look at this first example, CuCl2. This is a metal and a nonmetal, so we have an ionic compound. But Cu is a transition metal, so he can make a couple of different charges. So that means we have to work with our chlorine first before we can get to our copper. So from our periodic table, we know chlorine is a -1 ion, so that's going to be its oxidation number. But because there's 2 of them, that means the total oxidation number for all our chlorines present is -2 total. Because it's a neutral compound and it must equal 0, that means the total oxidation number for our copper must be +2, because +2 minus 2 gets me to 0. Since I only have 1 copper in my compound, that means the oxidation number for copper is just +2, because that would be its charge. So this would be kind of how you'd work with a little bit simpler transition metal. What if we have something that's a little bit more complex like Fe2O3? This is where we're going to have to use a couple of our rules. We learned on the last slide that oxygen gets an oxidation number of -2 in a compound. But because we've got 3 of them, that means our total oxidation number is -6. For us to equal 0, that means our iron must have a total of +6. So if we look at these, how many irons we have 2 irons in this compound. So if we do 6 divided by 2, that means each iron must be a +3 for oxidation number. So it's kind of like figuring out ion charge a little bit. So when we look at oxidation numbers, we only care about the individual oxidation number. We don't care about the total. So some of you guys may be able to get to these numbers without doing this bottom part, and that's completely fine. Whatever process you take is up to you. But some of you might want to keep track of the oxidation numbers down below to go ahead and make it a little bit easier for you. So whatever way you want to do, it's fine by me. So for a neutral compound, you must just have the oxidation numbers in total equal 0. Our last rule is about polyatomic ions. If you have a polyatomic ion, the sum of the oxidation numbers must equal the charge of the ion. So what that means is, if I'm looking at one of these polyatomics, like an SO4 2- or an NO2 -1 or an NH4 +1, my oxidation number total must equal the charge of the ion. So for this, I like to keep track of 3 things. I like to keep track of my oxidation number, which again is what we care about. This is the important part up here. I like to keep track of my total oxidation number. And I like to keep track of my ion charge. So I like to keep track of 3 things in this guy. So the first thing I'm going to do is I'm going to drop my ion charge down here. So I know that my ion charge is -2. So what that means is my total oxidation numbers must get me to -2 total. So if we look at our SO4, we don't have a rule for S's that we've learned, but we do have a rule for O's. We know from our third rule that oxygens and compounds get an oxidation number of -2. So I have a -2 for my oxygen. There's 4 of them present, so that means the total for my oxygens is -8. That means whatever I make my S has to get me to a -2. So if we look at this kind of mathematically, I need something -8 to get me to -2, and that would be +6, because +6 minus 8 gets us to a -2 total. So that means the S for its oxidation number would be +6. If we come over here to NO2, I'm trying to get to a total charge of -1. Again, we don't have a rule for N, but we do have a rule for O's. So I know my O is going to be a -2. I've got 2 of them, so its total is going to be -4. That means whatever I make my N has to get me to -1 left over. So if I think about it mathematically, if I do +3 and -4, that gets me to -1. So that means my N is going to have an oxidation number of +3. If I look at this last example, my ion charge is a +1. So that means between my total oxidation numbers, between my N's and my H's, I have to get to +1 total. Again, I don't have a rule for my N's, but I do have a rule for my H's. In Rule 4, we learned that H is always going to get an oxidation number of +4. So that means my total oxidation number for my H's is a total of +4. So whatever I make my N has to get me with 1 left over. So if I think about it mathematically, if I make this a -3, +4 minus 3 leaves me with +1. So that means my N gets me to a -3 then for my oxidation number. So when you're dealing with polyatomic ions, you have to do a little bit more kind of logical thinking and problem solving, because whatever your total is has to equal the ion charge. So if you know you have a -2 ion, your oxidation numbers have to add up to -2 in total. But again, remember, we only assign oxidation numbers for individual atoms. Now there's one other important thing that you can see happening in these last 2 examples. Especially for your nonmetals, they may not get the same oxidation number in every single compound. In this compound, my N is a +3 for its oxidation number. In this compound, my N is a -3 for its oxidation number. So your oxidation number is going to depend on the compound. It can change based on the compound that you're in. And that's something we're going to look at a lot tomorrow. So here's what's up next for you guys. You have these 5 examples in your notes. I'd like you guys with your partner, using the rules that you just learned, to go ahead and assign oxidation numbers to these 5 guys. Now remember, I only care about the individual oxidation number, not the totals and stuff. So my answer key has the individual oxidation numbers for you all. So that's going to be the first thing you're going to do. When you're done with that, show it to the sub, and then you guys can have the rest of the period to work on your homework. Your homework's on your calendars, but it's these problems right here, numbers 1, 3, and 4 on page 679, and that's going to be where we'll start class tomorrow. So go ahead and do these in your note packets, check them with the sub, and then go ahead and work on your homework. Again, if you've got any questions, please make sure you write them down, because I will be taking any and all questions you have tomorrow to start class. Have a great day, guys.